Easy as chips, Pythagorean triples. A squared plus b squared equals c squared. That is, 3 squared plus 4 squared equals 5 squared. Plain honesty, simple truth, easy understanding. The joy of finding things out for yourself. At the bottom and top of pages 29 and 30 of Fermat's Last Theorem by Simon Singh, you will read, a larger Pythagorean triple is 99 squared plus 4,900 squared equals 4,901 squared. Pythagorean triples become rarer as the numbers increase, and finding them becomes harder and harder. I think he's confused it with the primes. This is of course rubbish, as I shall demonstrate, and conceptually it is easy to envisage the infinite number of infinite series that are generated, but the articles that you can find fail to inform one of such. By 8 bags of triangular numbers t of rank n equals 1 to infinity, by 1 bag of infinitely many triangular numbers of rank 1 equals 1. Sort into lots of 8tn plus t1 for n equals 1 to infinity, where tn is equal to n squared plus n all divided by 2. 8tn plus 1 equals a square, that is, 8 times 10 plus 1 equals 81 equals 9 squared. This is equal to a squared in the first odd series of primitive Pythagorean triples, known as the Pythagorean series. Split a squared equals 81 equals 2n plus 1 into the base numbers b equals n and c equals n plus 1, so that 81 divided by 2 plus or minus a half equals 40 and 41. Thus 9 squared plus 40 squared equals 41 squared. It is also evident that the even base number b equals 4tn. And here are the first 9 triples of the Pythagorean series. It is easy to see how it can be extended infinitely many times. The difference c odd minus b even, denoted by delta c minus b, is equal to 1 for every triple in the Pythagorean series. The difference c odd minus a odd, denoted by delta c minus a, for the Pythagorean series form the sequence 2 times 1 squared, 2 times 2 squared, 2 times 3 squared, 2 times 4 squared, 2 times 5 squared, 2 times 6 squared, 2 times 7 squared, 2 times 8 squared, 2 times 9 squared, 2 times 10 squared, 2 times 11 squared, 2 times 12 squared, and so on and so forth. The first even series of primitive Pythagorean triples is known as the Platonic series. The difference c odd minus a odd, denoted by delta c minus a, is equal to 2 times 1 squared equals 2 for every triple in the Platonic series. The base numbers for the Platonic series are found as follows for n equals 2 to infinity. 1. A equals 4n squared minus 1. 2. B equals 4n. And 3. C equals 4n squared plus 1. Here are the first 9 triples of the Platonic series. Again, it is easy to show how it can be extended infinitely many times. The difference c odd minus b even, denoted by delta c minus b, for the Platonic series form the sequence 3 squared, 5 squared, 7 squared, 9 squared, 11 squared, 13 squared, 15 squared, 17 squared, 19 squared, 21 squared, 23 squared, and so on and so forth. This slide is a plot of the first few triples of the odd series vertically and of the even series horizontally. They have been ranked according to the magnitude of their constant series differences. Non-primitive triples must not be removed, or else order will be lost in the table. The can be seen from the table that the even series are orthogonal in the table to the odd series, so are just two sides of the same coin. In the odd series we keep the odd difference constant and vary the even difference between the two odd base numbers. In the even series we keep the even difference constant and vary the odd difference between large odd and the even base numbers. The table again shows the two sequences of base number differences, of which one of each must apply to every single one of the infinite number of primitive Pythagorean triples. Quadratic equation regression analysis using the base numbers c and b of a primitive Pythagorean triple series as data inputs will result in equations the algebra of which is given by the two expressions 1 and 2. These combine to give the quarter squares rule equation. We can calculate any primitive triple from the pair of base number differences. The value x in the equation is just 1 to infinity, and as we go up this series, the starting value x and step size increase are predictable. Most of the series contain non-primitive triples, where all three base numbers have a common factor, i.e. 6 squared plus 8 squared equals 10 squared, where all divide by 2 squared to give 3 squared plus 4 squared equals 5 squared. Non-primitives occur at positions dictated by the prime divisors of delta c minus b or delta c minus a, as appropriate. Only the series where delta c minus b equals 1 or 2 to the power 2n minus 1 are free from non-primitive triples. Non-primitives are essential for correct location of the series within the table. This slide shows the first 6 quadratic equations resulting from the first 6 ranked triple series. Now, who said finding bigger and bigger triples got harder and harder? As we can now easily calculate our own Pythagorean triples, we no longer need the meaningless tables of triples given to us by the mathematicians, due to their failure to give us the right information in the first place. End of video.